Hello, today we're going to do 7.3, which is diagonalization. So firstly, I'm going to give you a little bit idea what we're going to do, okay, before we introduce the detailed information. Now let's take a look at this linear system, dx2 dt, and this is a11 x1 plus a12 x2, a21 x1 plus a22 x2. Okay, and we can also write down this as x1, x2 derivative, which is matrix like this, and times x1, x2, right? Okay, for this linear system, we don't have B, it's called homogeneous, so we start from this one. And we want to solve this linear system, but you know x1 and x2, they are mixed together. It's pretty difficult to solve. So we want to change this into, we want to transform into another system, linear system. So we want to get a diagonal matrix, looks like transform into linear system like this one. So here we for example, we just say 2 and 3, okay, and 0, 0, just for random example, it may be some other number, but I just want to show you we want to do diagonal matrix, okay, here, and y1, y2. Let's take a look at this one, this system. This system equals to y1 prime, which is, so you can see we can do the product, it's just 2y1. And y2 prime, which is 3y2, right? So you can see this linear system is interesting because in the first equation, there is no y2. It's just like same as before, it's just an ordinary differential equation, first order linear differential equation. We learned this in chapter 1. We know how to solve this one easily, okay? For the second equation, we can also solve this. Actually, the solution to that one, they are like y1 equals e to the 2t, and the y2 equals e to the 3t, because you can, so we can see, do c1, c2, because you can test, when we take the derivative of y1, so y1 derivative, which is by chain rule 2c1 e to the 2t, which is just 2y1, right? And same thing for the y2. Actually, this is solution. If our linear system look like this with diagonal matrix here, so we can solve this linear system easily. Okay, so our goal, we want to do some transform, change our system into this kind of system, and then when after we find the solution, we transform back, find x, and then find x, transform back. Okay, something like that. So little bit idea. Now let's take a look at the procedure. Let's take a look. For our linear system, we can, okay, so at beginning, we want to solve this linear system, which is, let me write down this again, a21, a22, x1, x2, and if we write this in vector way, so that means x equals x1, x2, okay, so vector way, right? And we make this as the matrix A, so it's going to be like x derivative equals to A times x. This is the vector way of the linear system, right? X prime equals ax. So we want to solve this. Now let's see, if x equals sy, okay, we want to do some transform. Let's see, s equals xy, we plug this into the differential equation, what we can get. Okay, so from here we know, actually from here we know x prime equals sy prime, right? And when we plug in to the left side, that means sy prime equals ax, and x is what? Change x also into sy. Okay, so right now we change our original differential equation into this kind of differential equation. This one also only has y, no x anymore. And let's rewrite this little bit. We times s inverse on the both sides. Okay, let me do this in the next step. We times s inverse from left side. S inverse a s y, and we know this is just I because it's an identity, right? Become an identity matrix, and this identity matrix times y prime is just y prime itself. S inverse a s y. Okay, so we make this, we let this to be the b. So we say this equals by. So we can get a new linear system with y. So our goal, we want this to be diagonal matrix. Okay, and what we did, which kind of linear transform we did, like this way. We performed the listing. So if we can find such s, after we solve for y, we can find x later just by multiple the s. Okay, let's see the definition. Okay, you can see here b is s inverse as. Definition 1 it just means we have two matrices, A and B n by n matrices. We say A is similar to B if there exists an invertible matrix S invertible matrix S such that B equals S inverse AS. Okay, so in this case, we say A and B are similar. Let's take a look at example 1. If we have matrix A and we have a matrix B, so let's see, here is 19102. Verify that B equals S inverse AS, and where the S is given, S equals this one, 2, -3, -1, 2. Okay, we want to verify this. Because we want to verify B equals to S inverse AS, and B is given, we need to, S is also given, firstly we need to find the S inverse. S inverse, we learned two methods, adjoint method and Gauss-Jordan technique, right? Gauss-Jordan means like A matrix and I, and reduce this into I, here, A inverse. This is Gauss-Jordan technique. We skip the calculation here. 2, 3, 1, 2 is the inverse matrix for the S. And next, we do S inverse AS, we do the product. So that means S inverse times A times S, 2, 93, 91, 2. And C was the product. Okay, and after we perform the product, we can do the product. When we do the product of those two, So let's see. The first number should be negative 8 plus 9, so it should be 1. Something like this. All right, just do some product. Okay, and negative 20 plus 21 is also 1. Okay, and next, negative 4 plus 6 should be 2. Negative 10 plus 14, which is 4. And then do the product. So it's 2 minus 1, which is 1. Negative 3, add 2, so it should be negative 1. 4 minus 4, 0. 2 times negative 0, negative 6 plus 8, 2. So this is exactly same as B. Okay, so there exists such kind of S, and make A and B are similar, or make B equals S inverse AS. Okay, so let's see. We have next, we have a theorem. The theorem says the similar matrices have the same eigenvalue and eigenvectors. Let's see. Similar matrices have the same eigenvalue and same eigenvalues. Okay. Let's take a look at the proof. It's pretty easy to understand. Let's see. Similar matrix means what? Means B equals S inverse AS. Alright, they have this kind of relationship. And now let's see, how do we calculate eigenvalue? Do you still remember? So the eigenvalue for B should be like this, right? Make this equals 0. And we change the B into S inverse AS minus lambda I. Then we write I as S inverse S. Okay, so let's see. I don't know why it's disconnected. So let's see. Here, S inverse AS minus, we change I into S inverse times S, like this way. And next, we factor left side by S inverse and the right side by S. So become A minus lambda I times S. And by using the property here, AB determinant equals A determinant times B determinant. Okay, this is the property for the determinant. So we just write down this as S inverse determinant times A minus lambda I determinant times I S determinant. And they are all numbers. Definitely we can switch the order. Like we write down S together. And next we combine those together, those two, and this I determinant, which is 1 actually, right? So let's see. If we look at here, B minus lambda I determinant equals A minus lambda I, that means they have the same characteristic polynomial. So when we solve for eigenvalue, definitely we solve this for 0, right? We solve this for 0, but the polynomials are the same thing. Definitely they have the same eigenvalue. So for two similar matrices, they have the same eigenvalues. So next, for a matrix A, if A has eigenvalue as lambda 1, lambda 2, lambda n as eigenvalues, okay, can we find similar matrix B such that B equals diagonal matrix just with the same eigenvalue with A, and all the other numbers are 0. Okay, I know it's kind of difficult to understand here, but let's take a look at this simple example. I'm going to give you 2 by 2. For example, if B is diagonal matrix be this kind of form, just a random example, okay? And the 2 and the 3 here, I'm going to ask you, what are the eigenvalues? Can you see what's the eigenvalues? The eigenvalues actually is just a 2 and 3, because this is just 2 minus lambda, 3 minus lambda equals 0. So 2 and 3 are the eigenvalues, right? And because A and B are similar and they have the same eigenvalue, so let's see. The easiest matrix with the same eigenvalue is just kind of this form. Okay, so and those lambda, they are eigenvalues for A. So our goal, we want to find such kind of S and B, S inverse AS, okay, and such that B has the same eigenvalue with A. Let's take a look at theorem 2. An n by n matrix, A is similar to a diagonal matrix if and only if A is non-defective. Defective means if A is n by n matrix, A should has n independent eigenvectors, right? Non-defective. Okay. In such a case, if the eigenvectors are v1, v2, because non-defective, so matrix should have n eigenvectors. Okay, vn denotes n independent vectors. Okay, then S equals what? S just equals, we put all the eigenvectors as the column vector like this, and this gives us the matrix S, and if we do S inverse times A times S, this is going to give us a lambda 1, lambda 2, and lambda n diagonal matrix. Okay, the proof, I can give you a easy form of the proof. Let's just do the 2 by 2, for example. If A is 2 by 2 matrix and it has like a 2 eigenvectors, okay, and we say, and we do this AV equals, and because this is they are eigenvectors, right? Let's see, AV, and this equals what? AV1, AV2, and AV1 is lambda 1 V1 because V1 is the eigenvector, lambda is the eigenvalue, and same thing here is lambda 2 V2, right? And we can write down this into lambda 1 0 0 lambda 2 times V1 V2. Let's take a look. Is that true? So the first like a component number is going to be the product this one times this column, which is just lambda 1 v1, right? And the second are going to be lambda 2 v2. Okay, so actually you can see this is like a s equals, okay, here is like a b, and this vector is the s, because how we make s, so a just equals s inverse bs. And what is s? S is made by eigenvectors. And what is b? B is made by all the eigenvalues, diagonal matrix. Okay, so this is the proof. I'm going to show you in the example how to do this kind of problem. Don't worry too much, okay? I will show you detailed calculation. Okay, but before that, before the example, I'm going to give you a definition too. An n by n matrix is similar to a diagonal matrix is called diagonal legible to be. It can be diagonalized. Okay, let's see example 2. Verify given matrix 3 by 3 matrix is diagonalizable, and we want to find also S such that S inverse AS is diagonal matrix with all the eigenvalues in the diagonal position. Okay, so firstly, we want to verify it's diagonalizable. That means what? So let's take a look at the theorem 2. It's similar to a diagonal matrix if and only if it's non-defective. Okay, if it's non-defective, then it's diagonalizable because it's similar to a diagonal matrix, right? That means such kind of big matrix S can exist. So we just want to see if the matrix is A is defective or non-defective. So that is same as section 7.2. Okay, let's see. First step, we still need to find eigenvalues, and then we want to find the eigenvectors, and we want to see how many eigenvectors this matrix has. If this matrix has 3 eigenvectors, then it's non-defective. So 10 minus lambda. This is how we calculate eigenvalue. Okay, and here I just give you the simplified characteristic polynomial. Let's see what the eigenvalues are. Eigenvalues are 4 with multiplicity 2 and 3, right? Second step, calculate eigenvector. So for lambda equals 4, a minus lambda I equals 3 minus 4, negative 1, negative 2, 2, and then negative 3. Here negative 2 minus 4 should be negative 6, and 3, 6, 10 minus 4, which is also 6. So you can see this is easy to reduce into row echelon. 1, 2, 2, right? And the row 1 and the row 2 are totally proportional, so it should be 0. And the row 3, same thing, 0. And we have 2 free variables. We did this several times in the last section, right? So what's the eigenvector? S and T here, and what is V1? So V1 should be negative 2S minus 2T, but we want to rewrite this into linear combination of s and t. Okay, s times -2, 1, 0, right? And t times -2, 0, 1. So we get 2 eigenvectors here. Okay, and actually we can also tell from here, because we notice the dimension of the eigenspace, which is 2. Right, so we can say non-defective. But because if we want to find the diagonal matrix, definitely we need to find the other eigenvector, because we need one more eigenvector. So for lambda equals 3, plug in lambda equals 3. So I'm looking at the determinant when I calculate the eigenvalue. So -2, -2, -3, -2 minus, so -5. No, sorry, -2 minus -3, minus 3, yeah, -5. Okay, and then -6. Here should be 3, 6, 10 minus 3, 7. Okay, we need to simplify this a little bit. Lambda equals 3. Yeah, we are right. Everything's correct. Let's see. Let's do make the last row into 0 firstly. Okay. 1. Okay, and now I'm going to make the 3 to the beginning, okay, at the beginning. So can we make that easier? A little bit easier. I know this row and this row can cancel, so the last row has to be 0, right? And the second row we can be 0, 1, 1. And the first row you can leave 3, 5, 6, and then divide by 3. But I don't like to do that way. I want to make this easier. So I'm going to use this one to make this into 0. So times 5 added there, this is going to be 0. And this times 5 added there going to be -1. And then I'm going to get 1, 0, 1/3. Is that right? And 0, 1, 1, 0, 0, 0. So we have one free variable, s. So the vector equals what? The last one is free s, and the second component should be -s, and the first one should be -1/3 s, right? And then when we take this out, that becomes to -1/3, -1, and 1. You can leave this as eigenvector, but usually for the eigenvector, we don't like to write down rational number. So if we multiply this by 3, so it's kind of like we can write down this as -1, -3, and 3, like this way. And here we can factor like the same, like factor 1/3 out, something like that. Because, what method is this kind of number. You can use both, but this is better. Okay, just like kind of simplify. For example, if we have a eigenvector look like this, we want to write down this as 1 and 2. Okay, something like that way. We just want to write down simple way. So here we get 3 eigenvectors, right? And what is S? By using the theorem, S just equals to, if we put all the eigenvectors together, so let's see, the first two eigenvectors, -2, but we write down them as column way. So this is a V1 eigenvector, second vector, -2, 0, 1. This is second eigenvector, and the last one eigenvector, -1, -3, and 3. And what is S inverse AS, which is B? And B is going to be the diagonal matrix. And what's the diagonal matrix look like? So they have to be corresponding to each other. Corresponding to those vectors, the eigenvectors are 4. We cannot change the order, okay? You cannot write down 3 here. We have to, because those are the eigenvectors for eigenvalue 4. And the last eigenvalue is the eigenvector for 3. So we write down this way, okay? And this is how we find S and B. Okay, let's see. We can okay. Let me give you a remark. You can write down your S in another way. For example, if you write down your S into like -1, -3, 3, and then you write down the other like 2 eigenvectors. If you write down this way, so your B is going to be this diagonal matrix. So corresponding to that one is 3, 4, 4. Okay, does it make sense? Just they have to be corresponding to each other. Let's do the exercise. This is 2 by 2. It's pretty easy. Okay, matrix is -1, -2, -2, and 2. Let's tell if A is diagonalizable. And if A is diagonalizable, find S. Okay. I'm going to give the solution, but I want you to do this problem by yourself because it's a pretty easy one. Here's the solution. First step, I want to find the eigenvalue. Simplify. So eigenvalues are 3 and -2. Firstly, and next I want to find eigenvectors. For lambda equals 3, A minus lambda I. So it should be -1 minus 3, so -4, -2, and then 2 minus 3 should be -1. Simplify. Divide by 4, row 1, and row 2, they're proportional, so row 2 is going to be 0, and row 1 should be 1 and 1/2, right? Eigenvector. Eigenvector is going to be, second is free variable, and this 1/2 S, and if I factor the 1/2, let's factor S out firstly. 1/2 and 1. And then next I want to simplify this a little bit, so I want to write down this as 2, like this way. Okay, so I want to keep this vector as V1. Next, for lambda equals -2, find the eigenvector. -1 minus -2, so -1 plus 2, 1, -2. negative 2. 2 minus negative 2, so should be 4. 1, negative 2, 0, 0. And the one eigenvector should be, so this one, we can make this to be the t, and here should be 2t. Factor t out, so 2, 1. Right, so this is my second eigenvector. And this is 2 by 2 matrix, definitely non-defective, diagonalizable. And what is S? S equals 2. I write down the eigenvectors together, and 2, 1. And S inverse AS equals B. And what is the B? B is diagonal matrix with eigenvalue in the diagonal position, but corresponding to the order of S. I need to write down 3 here and negative 2 here. Okay, so that's all we need to know here. In the next class, we are going to do the same procedure like this, and after that we will start to solve the linear system of differential equation.